We're going to start the next session, which is on transforming education. And if you weren't in this session before, I'm Tom Richard. I direct the Penn State Institutes of Energy and the Environment, and I'm also a professor in agricultural and biological engineering. We have three speakers on this theme. I'll introduce them each at the beginning. This is one of the 5 themes in the university strategic plan. That's been the way we've organized Science Saturday, or blue and white. And this one, the sort of short version of transforming education, is that Penn State will seek to be a leader in the transformation of education, including enhancing access to it as it fulfills its land-grant mission in a 21st century context and continues to drive discovery-focused research across disciplines. So we have 3 speakers. The first is Dr. Mark Ballora, who's an associate professor of music technology in the School of Music and the School of Theater. Ballora teaches courses in music technology, history of electroacoustic music, music acoustics, and software programming for musicians. And he's done work to sonify data about water, climate, and the universe, offering people a chance to see data with their ears. Up second will be Dr. Paul Morgan, a professor in the Department of Education Policy Studies and director of the Center for Educational Disparities Research. Dr. Morgan's work focuses on early risk factors for learning difficulties. He also evaluates interventions to that may help young children experience greater academic success in the classroom. Dr. Justine Blanford is assistant professor in the Dutton E-Education Institute and the Department of Geography. Her work uses geographical information systems mapping data and spatial analysis to address questions about social, behavioral, and environmental factors that range from host-parasite interactions, vector-borne diseases, animal and human mobility, food, and sports analysis. So I'll let Mark come up and start, and then we'll move through each of the speakers. Mark, please welcome Mark Ballora.
Hi, thanks. I've got a graph I'd like to show you. How many of you have ever learned anything by looking at a graph before? Just about everybody. It's kind of an easy question. It's something that we do. We're taught to do this at an early age. My son is in the 2nd grade. He's learning how to read graphs. It's part of our cultural vocabulary. So this is what we do. It's pretty easy to read this. It measures the tide levels of the San Francisco Bay over 2 days, and it's easy to see how the water levels went up and down. It's easy if you can see it. What if you couldn't see it because of you were blind or you were visually impaired? How might I communicate this to you? Well, what if I took each of these data points and instead of mapping them to a line at a certain height, I mapped them to a musical pitch, and we'd get something like this. So instead of seeing a line that goes up and down, we would hear a melody that goes up and down. This is a real simple example of sonification, which has to do with taking information and mapping it to sound. Personally, I like to think of it as finding the music in science. Conceptually, it's very similar to visualization, but instead of mapping information to visual symbols, information is mapped to auditory symbols. And this is kind of becoming a thing in informatics. A great example is an astronomer named Wanda Diaz-Merced. She was rendered blind by an illness. And so she developed a software program that does what I just showed you. It allows her to listen to her graphs. And in her TED Talk, she describes quite compellingly how it has enabled her to work at the same level she worked at when she was sighted. And what's more, by listening to the graphs, she was able to detect the presence of electromagnetic resonances that nobody had been able to see in the graphs. And a lot of her sighted colleagues like to use the software because often there are patterns that can be more readily heard than can be seen. And to me, this is what's really interesting, because the eyes and the ears give us different information. So I just said pattern recognition. The ears are unsurpassed at this. Hearing little changes in pitches or rhythms is what their real strength is. The ear is also really good at tracking multiple streams of information, just as we can track multiple lines of counterpoint in a piece of chamber music. And speaking of music, think of how that affects us. As a species, we are extremely responsive to sound and music in a number of intangible ways. Think of how hearing your favorite song from 15 years ago is like opening this emotional time capsule that just takes you back to that time. So all of these things are the preoccupation of a group of people called the International Community for Auditory Display. And as a matter of fact, they're having their annual conference here at Penn State this summer. I will be chairing it, and I'm eager to show off Penn State to all of these people. And I wanted to show you what I'm going to be showing them, which is some work that I've done with a professor of meteorology here at Penn State named Jenni Evans. She works with tropical storms, and meteorologists who study tropical storms often look at satellite videos of these storms. Here's Hurricane Sandy, and you can see these on the NOAA website. So when we met, she was interested in what it would be like to add a sound dimension to movies like this. So what does that mean? What kind of data does she have? It's a little bit more complicated than that simple line graph I showed you just now. But one of the main ones is air pressure levels. When air pressure drops, the storm becomes more intense. So I synthesized this swirling, windy sound that gets faster when pressure levels drop. So just as a simple example, if we had a storm and the air pressure decreased and then increased again, we would get this. There's also the storm's location. There's latitude and longitude. So the longitude I can map to the left or to the right in the stereo field. The latitude I map by creating another sound layer. It's a repeated pinging sound, and the pitch gets higher as it gets closer to the equator. So if we had a storm that moved away from the equator and then back toward it again, we would get something like this. And last, there's symmetry. A rounder storm is more intense. Jenni likens it to an ice skater pulling her arms in and spinning faster. The same thing happens with a storm system. So I added a third layer. It's kind of a low growling, and it gets brighter to reflect greater symmetry. So this is an example of symmetry changing from less to more to less symmetrical again. So that's what these sound dimensions are. So if I apply the data from Hurricane Sandy to these dimensions and add a soundtrack to that video, we get something like this. So I've played these for a number of people. Actually, you can see these at the Earth and Mineral Science Museum. There's a little kiosk where you can choose from 11 storms. People tend to tell me that they find these videos a lot more engaging with the soundtrack. They use words like, it's a lot more visceral with the sound there. Jenni found that sometimes she found out things by listening to it. Sometimes the storms get more intense, but they don't get more symmetrical. And she can't see that as easily, but she can certainly hear it. So we thought that this was pretty interesting, and she thought, what if we took a more global view? We tend to think of a storm as a singular event at a particular location. What if we took a global map and we looked at what she called the spaghetti of storms that unfolded over a 12-month period? and we visualized and sonified that. So I got a little grant from my college, and we engaged Wade Shumaker from IST, and Jenni's grad assistant, Alex Kowaleski, helped us with the data, and we got this. So I'm real interested in this as an educational tool. We heard some talks earlier today about climate change and the importance of educating people about climate change. I would love to be able to contribute to that. Besides the fact that this might help students who are blind, or this might help students who are on the autism spectrum that might respond better to auditory than to visual cues, how might this work as just a general engagement factor in science education? My education friends tell me that if students have science presented in a sound/musical way to them, it may give them a more intuitive and holistic understanding of the material than they might get from visuals alone. We just heard a quiet period of the year. This is what Jenni said. We have quiet periods, but now I can actually hear them instead of just talk about them. What preoccupies me lately is this thought that what if we were to raise a generation of students to think of science as not just something that you look at, but also that you listen to? And taking the long view, how might that affect the research climate 20, 30, 40, 50 years down the line if we did that? I may not see that myself, but maybe my son will. So I appreciate all of you coming out today, and thanks to the Office of the Vice President for Research for letting me speak to you today. Thanks very much.